Okay, hello everybody. We are happy to have Doug Rosenberg with us today. He is author, teacher, and software guru, and he is interested in Agile in general, and his current interest in Parallel Agile, and he will tell us more about it today. Welcome.
So, welcome to all of you. Parallel Agile started in this classroom 4 years ago. What happened was every semester, Barry and Sue would invite me to come in and give a guest lecture to this class. And it was usually a lecture on UML and use cases because I've written some books on that stuff. And back in 2014, I had a project that I was interested in getting built, which was a geofenced mobile coupon system. And so when I got my once a semester email saying, do you want to come in and guest lecture? I replied, sure, I'll come in and guest lecture. And if you want, I can grade a couple of homework assignments for you. And I decided to assign my project as UML modeling homework. To that semester, there were 47 students in here. So I split my project into 47 use cases, handed out one use case to each of 47 students, and played email ping pong for about a month, I guess, month and a half, with 47 master students, each working a separate use case, which makes me, I don't know, maybe borderline insane, I'm not sure, but essentially what I expected is that we'd get a UML model done for this system, and I didn't really expect anything else. And about to when the first homework started coming in, and I thought, wow, this is going to go pretty well. And I suggested, you know, if you want, maybe we can assign an extra credit assignment, strictly optional, where everybody could prototype their use case for extra credit. And 29 students prototyped their use cases. And I said, well, this will be interesting, but it'll never integrate together. And then it integrated together. And we kind of said, how'd that happen? And 4 years later and 3 more test projects later, we're now calling it Parallel Agile. So basically the concept of Parallel Agile is one of the oldest maxims of software development is that you can't make software projects go faster by throwing more programmers at them. And this has pretty much been thought to be true since Fred Brooks wrote The Mythical Man Month back in the 60s or 70s, I don't know. And, you know, I guess my reaction is, well, maybe, because we seem to be having some success making software projects go faster by throwing more developers at them. And so we're going to talk about how and why that all works. But the basic premise of Parallel Agile is instead of this endless series of 2-week sprints that take a little bite-sized piece of work, do it in 2 weeks, and do the next 2 weeks, and do the next 2 weeks, without really too much upfront planning, just kind of scrumming your way down the rugby field, right? With Parallel Agile, we do a little more planning, but we can throw a lot more people into each phase of the development, and by doing that, we can get stuff done pretty fast and with kind of astoundingly low effort numbers. So let's just kind of jump in. So the central question here is it's widely thought to be impossible to be able to easily integrate the work of a whole bunch of developers working in parallel. Okay, but what if we could do that? What would the implications of that be? And the implications of that basically are, number one, we can accelerate projects by increasing the number of developers. That means we can get products to market faster without sacrificing quality, and that we can scale our projects not by stretching the calendar and adding more 2-week sprints, but actually by increasing the number of developers. And so what we've been seeing in our experiments thus far, we're about 4 years into this, is pretty significant cost savings and very radical schedule compression. So before you can put a system back together, you have to split it into pieces, right? So how do we split a system up to give one small piece of it to a whole bunch of different developers? The way we decided to do it 4 years ago in CS577 was we gave each developer a separate use case, and we let them analyze it, design it, and code it all the way through. So it isn't that big a trick to split a system into lots of use cases. Okay, we've known how to do that for a long time. I've spent 25 or 30 years in industry, traveling all over the world, teaching companies how to do that. And I've written a couple books on it. And so what we use as our default partitioning is each developer gets a use case. Okay, so that's not a inviolable rule that it has to be one use case per developer, but that's where we start. And if we get a big complex use case, we generally split it up. So when you do systems this way, you can take on as many use cases as you want in parallel, as long as you have enough developers to give one developer to each use case. So usually, because we work with small use cases, like around 2 paragraphs of English text as a use case narrative, usually one developer can complete one of those use cases in a month. And so the steps, and they're in my book, Use Case Driven Object Modeling, you write a narrative description. We do a model view controller decomposition for each use case. So we describe the use case in English, sunny day scenario, rainy day scenarios, and then we say what are the screens, what's the data, what's the logic. That's basically MVC. And then we do detailed object-oriented design, sequence diagrams, state machines. And then I'm not a big TDD guy. The way I learned programming was first you code it and then you test it. Nowadays, first you test it, you make sure the test fails, then you write code, you make sure the test passes. It's okay if you like it. You can do it that way. For me, it's a lot of extra work. But the key to integrating all of this is that when you decompose a system into use cases, multiple use cases can share the same domain object. Okay. So in terms of model view controller, the domain objects would be the model part. So my use case might have that part of the model, and your use case might have that part of the model. And in that case, we're able to integrate the work across these use cases using some techniques that are pretty popular these days, basically REST APIs. The bottom line of this is that taking the system apart into use cases is not that big a deal, but putting that system back together once you've taken it apart is something that not very many people have really tried to do that I'm aware of. So the legend is that all the king's horses and all the king's men can't put Humpty Dumpty back together again, but using microservices and REST APIs, we seem to be putting Humpty Dumpty back together again. I'm working pretty closely with Professor Bain on Parallel Agile. He, of course, is the creator of the ICSM. I'm going to assume you guys have all been introduced to ICSM. So ICSM has all these 4 and 5 syllable names for different phases. Like, I guess they're not all long syllables, but they're not real intuitive, like the valuation phase. And, and I'm kind of like, I went in his office and I said, I think what you're doing with ICSM is you're basically saying kind of first you do a proof of concept and then you do a minimum viable product and then you get it ready for release. He's like, yeah, that's pretty close. So my simplified version of ICSM is we do 3 phases, okay? And the 3 phases are proof of concept. And when we do proof of concept, we mostly use prototyping, okay? We can do use case modeling, but a lot of times when you're doing proof of concept, you're poking around at unknown technology, high-risk stuff. We were poking at, geofencing and voice recognition and augmented reality and stuff like that. And sometimes you have to prototype it to figure out what you can do, and you need to figure out what you can do before you write a set of requirements for a product. Okay, so we do heavy prototyping in the proof of concept phase, but we don't ship the prototypes. One way to look at agile development is you jump in, start writing code, and that code gets shipped unless you refactor it, right? So we don't do design by refactoring. We do design by design, which means in the minimum viable product phase, we actually do pretty careful use case modeling. And that especially includes modeling the rainy day scenarios in addition to the sunny day scenarios. Because where many software projects get in trouble is they do the easy part, which is the sunny day scenario, and they don't really want to think about the hard part, which is all the exception cases and error cases and stuff like that. And the Agile community has invented one of my favorite terms for this. They call it technical debt, right? So it's like, if we don't want to bother thinking about that now, that goes in the technical debt bucket, right? So what you get is you get a bunch of sunny day scenarios released into the field, and then a big bucket of technical debt. And then later you go back and think somebody else has to think about what to do with that big bucket of technical debt, right? I'm not a big fan of that approach. So I like to identify my requirements, model my use cases carefully, do a careful design, and then I focus on acceptance testing the hell out of it, okay? So again, I'm a little different from the way most of the Agile community works. The Agile community tends to focus heavily on unit testing. So they're doing the write the test, make the test fail, write the code, make the test pass, all of this. And what they get is they get a whole bunch of unit tests. And they typically, if they're ignoring their rainy day scenarios, they get a whole bunch of unit tests for sunny day scenarios. And then all the rainy day scenarios are in the technical debt bucket, right? And so this doesn't really guarantee you a high quality piece of software at the end, okay? Because mostly where software breaks is the rainy day scenarios. So we focus in the initial release phase on performance tuning, optimization, and acceptance testing, okay? So again, it's first you prototype it, then you design it, then you acceptance test it, okay? What this really does is it changes the whole ballgame in terms of, since you've done a little bit more planning, you don't have to bite off a little tiny 2-week chunk. You can think in a little bit longer horizon than 2 weeks by putting more planning back in. And then you can have larger teams of developers collaborate. And again, our initial expectations were that this stuff wouldn't really integrate back together, but in the projects we've been doing, it has integrated without too much trouble. It means you can take on small, medium, and pretty decent-sized projects in around 3 months, because we take each of these phases, since everybody's got their own use case and everybody can do their use case in a month or less. You get a month here, a month there, a month there, and in 3 months you go from nothing to a system that's been prototyped, designed, acceptance tested, optimized, and ready to ship, okay? That's kind of cool. I spent a lot of time talking to Professor Boehm about scalability, like what's the limits to this, and I put this bullet on here specifically for him because he looks at me and he says, if you're going to tell me you can do a whole ballistic missile defense system in 3 months across all the joint services, I'm going to tell you you're lying. And so, no, I'm not claiming we can do that, okay? What I am claiming is if I have a big system that might take, let's say, 800 developers across multiple companies, I could split that into maybe 8 100-developer parallel agile teams and make a pretty good run at it. But no, I'm not claiming we can even figure out what the requirements are for a ballistic missile defense system in 3 months. So please accept my qualifier. It's not unlimited. I'm not sure we know where the limits to it are yet. In my head, I'm good saying about 100 developers at a time is something that I think is manageable. You can do a lot of software with 100 developers working in parallel. A lot. Okay, you can do big systems. And then one of the things that we've discovered that's a common thing between the way I've been teaching these classes and running these projects and work that Professor Boehm has done both at TRW on these huge mega multi-million line projects that he used to run and that's in the ICSM is that we like to have a test team working concurrently with the developer team. And I just realized about 10 minutes ago that your TA, Ali here, was on one of my projects 3 years ago, and he was on my test team when we were figuring out this pattern of having the test team work concurrently with the developers. We'll talk about this geofence coupon app. But I had like 3 or 4 of you guys on the test team, right? And so I had a bunch of people writing code, and then we were doing, if I remember, geofence testing. We were testing several different commercial geofencing products. We wound up building our own. But we had a little test course around campus that you probably helped put together that had geofences, like at Tommy Trojan and, different places. And we'd have people walking around with their phones to see if they could trigger the geofences. So having this test team working concurrently with the developers is a useful thing. So we've been getting pretty significant overall cost savings, and if you take student hours and normalize them into full-time equivalent hours, really pretty radical compression in terms of schedule. And as an example of the 4 projects that I'm going to show you a little bit later on in this talk, I'm not sure any of them, so 2 of them have involved about 75 students working across multiple semesters. I don't think any of those projects have exceeded more than, I'll say, 2 to 3 man years, person years of full-time effort. And we've built some pretty significant size systems for those effort numbers. So there's a couple reasons why we're getting these numbers. Really, if you look at computing and you look at the acceleration in compute power, the cloud, GPUs, everything else, it's all parallel processing, right? So all the hardware stuff that's being done to accelerate performance in computing is being done with parallelism, okay? I'll just throw 15 CPUs at it. But people haven't really been taking that approach with software development. Parallel Agile is trying to take that kind of thinking and apply it to software engineering. And we're getting kind of analogous numbers, pretty similar compression. By being able to work in parallel, you can accelerate things pretty quickly. I'm an electrical engineering guy. I got my degree from here in 1980, by the way. And a short story, when I graduated from here, I went to work at what was then TRW, which is now part of Northrop Grumman. And I was a junior programmer, and the chief scientist of TRW was a guy named Barry Bain. So he was like God in the 20th floor office. I had a basement office, right? But he and I go back a ways in industry. I once asked him, did he know my boss? No. Did he know my boss's boss? No. Did you know my boss's boss's boss? Yeah, I think I kind of remember him, right? So it's a big honor for me to get to work with him on this stuff. A huge honor for me. So, and you guys are all really lucky to have him as your professor. I'm going to tell you, you're really lucky to have him as your professor. There's few people in the world that have his depth of experience at software. Few, if any. So basically, Parallel Agile gets to code really early with prototyping, and by getting to code early, we're kind of true to the spirit of being Agile, because what the Agile people basically came out 15 or 20 years ago and said is, if you just sit there and analyze and design forever, you get analysis paralysis, you don't build anything, and you don't really know what's going on. And, they're right about a lot of that, but the way they did it, I'm not so sure I like it. So we're both agile and disciplined at the same time, which is that we don't just ship the first thing we code and then refactor it to death. We actually design it really carefully. And that has, design has got lost in the agile, and now it's agile and continuous integration, continuous delivery. I'm working a consulting contract that's doing continuous delivery now. I invented a new term since I started working there. I call it hotfix-driven development. They've optimized their whole development process to respond to buggy software getting out in the field. Those things get responded to right away. Everything else goes on the slow queue. I'm not a big hotfix-driven guy, so I like to design carefully. The thing is, if you have a whole bunch of people designing their use cases in parallel, it doesn't take a lot of time, because it only really takes a few hours to analyze a use case. And so you can take that few hours and multiply it out times 50, okay? And it only took a few hours on the calendar, but you got a whole lot of design work done, right, in parallel. It's not big design up front because the design doesn't take a long time. And the other thing is, before we start doing a whole lot of design, we usually prototype stuff. So anything that's a high-risk use case, we prototype it first. So now we come down to the, hopefully I've convinced you that there's some merit to integrating the work of many developers working in parallel. And now is the $6 million question, which is, how do you do that? So basically how you do that is you take the same development strategies that are being used for business-to-business integration, which is microservices and REST APIs, okay? So, Facebook has their API, Twitter has their API, Google has API, there's a Google Maps API, there's an API for everything, right? And so you can put apps together by making API calls into these things, and you can integrate work that's been done by different businesses into your code, okay? That's pretty standard now. So if you want to think about how Parallel Agile does this, imagine that every business that's developing a piece of code is a really small business. Imagine that business is a one-person independent contractor, okay? So now I have 20 businesses collaborating together, but each of those businesses are a single developer, right? I can still integrate the work with REST APIs, okay? So basically, what we've developed is a code generator that takes a domain model. You guys all know what a domain model is? But a domain model is basically a model of the problem domain that you're trying to address. And it's represented in UML as a class diagram. Okay, so we basically take a class diagram that represents the problem domain, and you can put one of these together in 2 or 3 hours usually, even for a pretty big system. And we turn each of the classes on that diagram into a NoSQL collection. We're right now targeting MongoDB and Node.js. Okay, so I take my class diagram, every box on the class diagram becomes a Mongo collection. We code generate the database access functions. So they call them CRUD functions. You guys know that term, create, read, update, delete. So there's create one, create many, read one, read many. There's a whole bunch of them, right? It's more than just 4. There's about like 8. So we code generate the Mongo collection, code generate the get, put, post code, because everything with NoSQL databases is get, put, post. And then we take each of those database access functions and wrap it in a Node.js API. Okay. And you guys know Bo Wang? Do you know Bo Wang? I know Oslo knows him. He said you guys know him, but he used to TA in this class. Anyway, that's his PhD research site code generator. And I think some of you may be using it by now, I don't know. So we call that executable domain models. Okay. And executable domain models basically takes the ideas that are in a pretty well-respected book called Domain-Driven Design. It talks about how to find the sort of simple problem space model underneath all your code. And it kind of marries it up with a book called Executable UML, which is why don't we take this UML stuff and actually make it runnable. And so if you want to understand what Bo's PhD research is, in a nutshell, it's basically that and that fused together. So we model a problem domain on a UML class diagram. Every domain object becomes a NoSQL collection. All the database access functions are code generated. Then they're wrapped in a REST API. And here's the key, is that we do this right at the beginning of the project. So right at project inception, we say model the problem domain and then code generate it. And we immediately have sort of an executable backbone or backplane that everybody's code can plug into. Okay? And that includes prototype code. So when we prototype, we're not just prototyping screens, we're prototyping against a live database. And the reason that we target NoSQL databases is because if you're going to code generate this at the beginning of your project, you haven't really figured out what all the database schemas are yet. Okay? And the difference between NoSQL databases and SQL databases is that with SQL databases, you have to know what all the columns are. But with NoSQL databases, whatever JSON structure you throw in there gets handled by the database. So that means you can have different prototypes with different JSON structures all working, okay? You have to merge them together after you leave the prototyping phase before you go into the real design. But you can do basically evolutionary database schema design. Okay, so you can evolve your database schema by having 6 people prototype it, different use cases that use that object. And at the end of it, you just merge that schema together and you figured out your schema. Maybe quicker than you could have done it sitting in a room, scratching your head on the whiteboard, trying to figure out all the schema in advance, because you wouldn't have got it right anyway. So once we do this code generation, then we have our developer-to-developer integration using these REST APIs, and it works just fine. And we've had very few issues on integrating anything. Okay, so the integration issues that we thought going into this would be impossible have proven to be not even significant. So we think this is pretty cool stuff. So this saves you a lot of time because there's a lot of code that you don't have to write. Here's a use case. This is actually from the KarmaCam project that Oslo worked on. This is the use case that glues together our mobile app and our server stuff. And you upload a video to the cloud over here, and it sends you an email back with a link so you can play the video. Everything in this orange box is kind of back-end server stuff, everything on the side of Node.js here. You don't have to write that stuff. So typically this may be 20 to 40% of your application is making all the server-side stuff work. But because all the server-side stuff is code-generated when you start, you don't have to write that. So that's a big savings that you get, and that's one of the big factors in the cost and schedule improvements that we're getting. Okay, so you really never have to write a line of Mongo code unless you're doing some complex server-side stuff. There's exceptions, okay, but the typical case where you're just uploading something from the phone, storing it in the cloud, pulling it out of the cloud, looking at it on your phone, which is a lot of what modern software development does. And not just your phone, but in a web browser, okay, on a web app. All that integration just happens, and you don't have to write the database access stuff. So we're trying to do feedback-driven project management combined with plan-driven design, combined with the ICSM spiral model evidence-driven lifecycle. And so on the Agile project management side, we kind of don't think there's much point fighting a battle with the Scrum people about user stories and tasks and epics. We just kind of accept that that's how projects are managed. But what we did was we took that paradigm of epics and user stories and tasks, and we found a UML profile that does that, and we keep the sprint plans in the UML model along with the technical design. Okay, so that allows us to start linking things together, like if your user stories is such a misleading name because more often your user stories are requirements than they are scenarios. Sometimes they're scenarios, sometimes they're requirements. But we can start linking everything together in the same UML model this way. And then we can do a couple different kinds of estimation with the UML model. We can do bottom-up estimation that says I'm going to take the work for each of these tasks and roll them up, and that's the total number of, it's kind of like story points that you get for the user story. And then you can sum those up into the epics, and you can kind of do bottom-up estimation on a task-by-task basis that way. Or if you have a good use case decomposition, you can do top-down estimates from the model view controller breakdown. So it's Agile project management in this way. And then here's a book that you may have heard of with an author that I know you've heard of, which is Balancing Agility and Discipline, and that's really what we're trying to do with this approach. The typical way this breaks down is there's kind of 2 big schools of thought on how to develop software. There's the plan-driven approaches, and then there's the feedback-driven approaches. Okay, and so you get different failure modes on either end of the spectrum. And when I mean failure, I mean the cost becomes prohibitive. Okay, so on the planning side, if you get into analysis paralysis and you just spend all your time planning and no time building anything, that's really expensive. And on the Agile side, if you start just completely under-planned code, build it and ship it, and then deal with the hot fixes later, you get hotfix-driven development over here. That's also really expensive. So somewhere in the middle is this cost minimum of just enough planning and just enough feedback. And that's, I had a previous company called Iconics, and we kind of targeted this cost minimum for about 25 years. We've kind of done some enhancements with Parallel Agile, but we think we're pretty close to this cost minimum. If you know a more cost-effective way to develop software, please tell me about it, because I want to know. So again, to tie this back into the spiral model, at the inception phase, that's kind of part of this executable domain model. We model the problem domain, make it executable, and then we go into proof of concept where we start prototyping. We take the results of the prototype, say, yeah, that worked, that didn't work. We'll keep the stuff that worked. We'll toss the stuff that didn't work. And then we do our MVP design, and then we go into heavy-duty acceptance testing before we ship stuff. Okay. And each of these phases takes around a month. And at the end of 3 months, you have basically gone from 0 to ready to ship. So another one of my books is called Design-Driven Testing, and it has strategies in it for when you write use cases and you detail out the sunny and rainy day paths through that use case, you have to test all those branches. It has strategies for testing all your requirements. And what we've been doing on our projects is having the test team work concurrently with the development team. The bottom line is, I guess I should stop and see if anybody has any questions. Anybody have any questions yet? Yeah?
The 3 months period does not include the initial time, right?
Yeah, so it's basically, what does the 3 months include, right? It includes your initial prototyping, then it includes your design, then it includes your test phase. So the way we got this from our student projects is that we were doing these projects across multiple semesters. Okay, so you were in this 3rd semester maybe of the mobile coupon project, 2nd or 3rd semester, I don't remember. But on the student projects, we had students working between 5 and 15 hours a week, okay, for 1 semester. If you normalize that out to full-time 40-hour weeks, it collapses down to about a month. That's where the month comes from. It's not a 1 month hard time box. I'm not a big fan of time boxes because I think time boxes cause people to rush their code and not handle all the rainy day cases, and it gets stuff out the door, but there's just all hell to pay later. Okay, so this is not like it's 3 hard set 1 month time boxes. It's when everybody gets their use case done, we can move to the next. So everything kind of goes faster when you work in parallel. And just to reiterate, we're developing in parallel. It's typically 1 use case per developer. When we have things like, I got a whole bunch of complex server-side logic, we can split that use case, and we'd have maybe some server-side controllers, and maybe 1 developer would get a controller instead of getting the whole use case. You basically split it into chunks where no chunk is going to take more than a month, okay? And you throw as many people at it as you can throw at it, right, as it needs. And then we integrate in parallel. Basically, the integration happens because everybody's calling the same API. I create this object, you consume that object, okay, or collection, right? I may put 3,000 records in there. You may read all those records. The other thing that the API gets for you, a couple things. One is even your early prototypes get to access a live database, and you learn a lot more when you're accessing a live database than if you're just storyboarding screens, okay? And the other is that REST APIs are language and platform neutral, which means you can have an iOS client, an Android client, an Angular JS client, a Unity 3D client, and we've actually done all of those. And then we test in parallel. The test team works currently with the development team. And it's absolutely never too early to start acceptance testing. That's to kind of put all of this on one slide. You start the project by drawing a domain model, drawing some use case diagrams, generating the database code and APIs from the domain model. You organize your use cases into groups, and you assign developers to the use cases. Okay, that's the inception phase of the project. It takes a couple of days, maybe, okay, depending on the size of the project. Then you go into, and these were the original 2 homework assignments that I handed out in this class in 2014, were called Build the Right System and Build the System Right. So Build the Right System is pretty much the analysis part. For high-risk stuff, we always prototype it. And then for all use cases, we're going to storyboard out the screens, research our requirements, write the sunny and rainy day behavior, and decompose those use cases into models, views, and controllers. Okay? So I want to know what's the data, what's the screens, what's the logic. That's MVC. And then I go into design. And my preferred way to do design is model-driven. So I use sequence diagrams and state machines and things like that. A lot of people these days like the feedback-driven TDD stuff. It's okay. The truth is, as long as you get this right, you can do design either way. Okay? I personally think this one's faster and gets better results. Your mileage may vary. Hardcore TDD people will debate me until they're blue in the face. That's okay. They can do it that way. And then this is from my design-driven testing book. In design-driven testing, we have strategies for both developer testing and QA testing. In Parallel Agile, we mostly focus on the top part of this, and that's testing all the requirements and testing all the sunny and rainy day paths through the use cases. And this one's worth talking about. Essentially, here's a use case. This is actually out of the book. But the premise of scenario testing is I've got one sunny day path all the way through here, and then I've got rainy day path number 1, rainy day path number 2, rainy day path number 3. Okay? So to test this use case, I need at least 4 test scripts. Okay? One that goes through that sequence, one that goes through that sequence, one that goes through that, and one that goes through that. So we built some automation into Spark's Enterprise Architect, which is the UML modeling tool that I like the best. It actually will take the use case description and generate all of those test paths for you. And we find this to be really useful. Because the big thing with testing is to make sure you haven't forgot anything. If you test your software this way, you don't get very many hot fixes coming back because you've anticipated the failure modes, the edge cases, the corner cases, and you've tested them before you ever ship anything. So now we get to the more interesting part, which is, well, okay, that's a whole bunch of nice theory, but you know the difference between theory and practice is that in theory there's no difference between theory and practice, and in practice there is. And I'm a practice guy, so to me I got to prove that it works in practice before I think it's worth anything. And so we have done over the past 4 years so far 4 test projects. Those projects have involved, in round numbers, 200 master students, 2 of whom are sitting in this room at least, Oslo and Ali. The 4 projects are location-based advertising, which we did with about 75 students, picture sharing, which was about 15 students, KarmaCam, which I'm going to demo for you, and then my game project, Tiki Man Go. About 75 students on KarmaCam, 25 students on Tiki Man, 75 on location-based advertising. So it isn't the end of proving that it works, but it's a pretty good beginning to proving that it works. And we're actually now just about to start some industry tests of this. The company that I'm consulting for has a big, huge legacy database system with a database that was actually initially developed. Well, the product was initially developed some 30 years ago using very mature database technology that was 20 years old at the time. So the database technology that they're in now is 50 years old, and they have a really hard time finding developers who know how to keep it running. And we are about to generate for them MongoDB and Node.js. And we're going to see how that goes. So we're starting industry testing now. So let's talk about the 4 projects. So location-based advertising was the first one that we started in here. It was 2 homework assignments, and we had 47 students writing use cases, and 29 of them decided to do the extra credit prototype code. We continued to run that for a couple of more semesters until we had about 75 students total. Ali was one of those students. And at the end of I think it was probably 4 semesters that we ran the project, we added up the total aggregate number of developer hours, and it was about 2 person years total across 75 students. And we kind of said, that's kind of interesting. And then it was on this project where we didn't have our code generator yet, but we came up with the concept for the code generator. It started out as a design pattern on the location-based advertising project. So what this project was, and we actually built it kind of all the way through to completion, found a client for it, was not a commercial success. I'll tell you a little bit about why. We may still resurrect it at some point. But the basic concept is I have a phone and I like to get discounts at restaurants and things like that, right? So I can sign up, get this app on my phone, and as I walk around or drive around, restaurants can basically send coupons to me when I'm right near the front door. Okay, restaurants and stores. Kind of pretty interesting concept. So we have a web app where a store owner can go in, design a coupon, publish the coupon, and specify a geofence for that coupon. And then when you take your phone out and you get inside that geofence, a coupon shows up on your phone. And then when you redeem the coupon, it actually generates a transaction. So we bill you kind of like with a phone call, right? So we bill the store for every coupon that gets redeemed. And so this was the concept. And I sort of had this bug to get this system designed when I walked into this class 4 years ago and said, why don't you let me grade a couple homework assignments for you? So this was the original use case partitioning. And so there was an iPhone app and an Android app and the partner website where they designed the coupons, and then the server that, handled broadcasting out the coupons. And this turned into 47 use cases. They were I had to stretch a little bit to get it to 47, so the Android ones and the iPhone ones were kind of redundant. Same use case, different platform. And then we prototyped different geofencing solutions. So this system had a kind of a really interesting technical problem at its core. You don't see a lot of systems like this, even now, 4 years later. There isn't really a killer mobile coupon app, geofence mobile coupon app. One of the reasons is a couple of the requirements are pretty hard. And those requirements are whatever you build has to sit in the background on your phone and run while your other phone apps are running, okay? And you just kind of have to leave it running all day long. But with geofencing, you kind of want to use the GPS. And if you leave a background app running GPS code on your phone, if your Pocket doesn't catch fire, first, your phone's going to run out of battery in about 45 minutes. But if you have a coupon app and your app is asleep because it's not using the GPS and you walk past the store and you don't get the coupon, it's no good, right? So what you need is essentially background capable Wi-Fi power consumption, GPS accuracy, geofencing, okay? And most of the effort on this project was in building that. There's another student in the PhD program named Kan Chi. I don't know if you guys know Kan, but Kan built our Android. We built this project in Cordova, PhoneGap. So we had one code baseline. We built our own geofencing plugin. And we tested, I think it was 3 different commercial geofencing solutions that claimed to offer power-safe, background-friendly geofencing. The problem with all these the commercial geofencing solutions that we found were that they tried to do stuff like Wi-Fi triangulation to avoid using the GPS, and they weren't responsive enough. So you'd walk past the store, get like around the corner 2 blocks later, and then the coupon would come in. Okay, it's like, nope, can't use it. So Ali, who just left, was involved in testing all of these different geofencing solutions that we built, and we prototyped a bunch of them. And finally, the one that we built outperformed all of them, and we had plus 95% accurate coupon delivery. We actually got to 100% around Santa Monica. So that was pretty good, technically. The technologies we were using here, we were using Cassandra for our database, jQuery Mobile for our both the mobile app and web app, and then Node.js to glue everything together. So this is also where we came up with the design pattern for executable domain models. So here was our domain model. We had a partner, which was like a store owner. It had a place, which was a store. That place had an offer associated with it. The place had a geofence associated with it. And then when you'd redeem the coupon, you'd get a transaction. Those were aggregated into your bill, and then we send the bill to the partner. Okay? Not too complicated of a domain model. These attributes on the UML classes, you can read it maybe a little bit better over here. These attributes translated into that JSON structure. Okay? So we basically were teaching everybody, it's like, and we started actually was literally with this thing, it was geofence.js, and we handed out a piece of code called here's geofence.js, and it had create, read, update, delete on it. And we just told everybody, you know, for whatever object you're using, follow this design pattern, okay? So here's a JSON structure, do create, read, update, delete, that calls put, post, get, okay, which is what is inside NoSQL databases. And this worked really well doing it manually, and it worked well enough that we decided we could just take that whole design pattern and automate it in a code generator. Because after this happened, Bo actually turned all of this into Node.js so that we could access it from both the web app and the mobile app, right? Android, iPhone. So we considered this pretty much a technical success. We didn't really quite get to finish performance tuning it in terms of the user interface. So it was a little bit sluggish because I had a really impatient client who had gone around and promised all of his advertisers back like 4 months before we had it finished that, damn it, it'll be done in July. And, you know, on August 1st, I think I had 15 text messages on my phone about how come it hasn't shipped yet. And I basically said, okay, you want to ship it today? We'll ship it today. You know, I think we still need to tune it a little bit, but you want it shipped today? We're going to ship it today. And so we did, and he never quite recognized that, you know, I'm doing this with students. I don't really have any full-time. I mean, he knew, but he didn't act that way, right? And it's like, it's a pretty bad idea in general with software to put your release date in concrete before you finished your testing, okay? I don't recommend doing it. At the end of the day, the guy who we did it with, he has the Santa Monica local tourist maps. I live in Santa Monica, so that's how that happened. And you know, he was generating about 10 app downloads a day. And it's kind of like, this ain't 10 app downloads a day is not worth this effort. So we just kind of pulled the plug on it. But it may still get resurrected. The lessons from location-based advertising is that I call it a successful failure because we learned a lot from it. First thing we learned is that, yeah, we can do massively parallel development, that we can integrate this work using these REST APIs. And this total effort number, about 2 person years for 75 developers, is something that I considered to be sort of an eye-popping number. And we figured out that we could build this code generator, and 2 of the students that were on that project got into the PhD program. That's Bo and Con. Kind of around the end of the first semester when we put the 29 prototypes together and it actually worked, we kind of looked at each other and said, that's not supposed to happen, okay? We're not supposed to be able to take, and in this class, you're not really, I mean, I guess they allow team projects, but most students are supposed to do their homework individually without sharing, right? So the academic restrictions are everyone does their own homework. So it's not only, you know, we had 29 developers, but there's actually restrictions on them working together, right? And it's like, that's not supposed to work. Maybe we should try it again. So we tried again with a project called PicShare. This was about, I don't know, 12 or 15 students. They were really 577 students that I was mentoring one night a week. I don't want to spend too much time on it, but this was a photo sharing application. Go to a party, upload pictures, put a hashtag on it. But we taught them in the mentoring, we taught them to do careful design, like write their use cases out, write the rainy day scenarios, design all the stuff. They didn't have the code generator, but they used something called Parse Framework, which kind of took care of the back end. And at the end of it, I basically mentored these students first semester, and then I really didn't have anything to do with them in the second semester at all. They were just on their own. It took them 40 days to code their iOS app, which sounds, okay, 40 days to code the iOS app, not really that complicated an app. But then you think about what is that in full-time numbers. These kids are working 10 to 15 hours a week. So if you normalize that out to what's the full-time equivalent, about 2 weeks worth of full-time coding effort on that project, okay? That's pretty good. One of the things we taught them was how to do the acceptance testing stuff. So this is one of their test cases. And you can see all these off-nominal cases here. Whoops. The off-nominal cases were tested in their app, okay? That's something that when you go out in industry, you often don't see that, right? They just do the sunny day scenario, ship it, and the off-nominal cases come in as hot fixes. That worked pretty good. Parse Framework sort of took care of the back end for you, so it kind of further validated this concept of executable domain models. We had a false start on that project that some of the TAs in here gave these students the absolutely wrong guidance on how to break a use case into a model view controller. And so I had 10 students come to my DR class, all having made the same mistakes on their diagrams. I'm like, why are you guys all doing this way? And they're like, that's what our TAs told us to do. So that took half a semester to unravel all of that. And basically, it was a pretty good result. But the most interesting thing about this project is that I was working with a team that was uploading media files to the cloud. And it happened that while I was uploading these media files to the cloud, I was working a consulting contract down near LA Airport with a big telecom company that does set-top boxes. You can probably guess who they are. And I had this really nasty commute every day. And one day when I was about to get on the Santa Monica freeway, a car that was 2 lanes over to my right makes a totally illegal U-turn in the intersection right in front of me just as I was about to go through the arrow. And luckily, I had just had 2 cups of coffee, so I hit the brake and I didn't hit the guy. I would have totally T-boned him if I hit him. But after I stopped swearing at him, I decided, we need an app like this picture sharing app that uploads video instead of still images. And that was when I came up with the idea for KarmaCam, which we've been working on for the last couple of years now. So before I go too much into that, I can give you a quick demo of KarmaCam. So let's go put this video full screen. So you're going to see me about to get hit by a truck. I drive around with this app on my dashboard a lot. This truck had no idea until right then that I was in his lane. Or I was in my lane, and the lane that he was claiming for his own. So the idea of KarmaCam is we'd like to be able to go in and get the license plate number of that truck, which we did here, because we have video. So if I hit this capture button, I can go in, scroll this video forward to right about where he almost hit me. Then I can hit capture. And now I can zoom in and get his license plate number. And Oslo, who's sitting right over here, built some stuff. Oh, it's in the other build of it, but we can actually enhance the image quality on here. We can change the brightness and the saturation and the contrast, okay, using stuff that he built. So he was a key part of this project last semester. So we're uploading metadata about the location, the time, we're categorizing it. So that's KarmaCam. Basically, uploading media files to the cloud is very interesting. This was our first test of the real full Parallel Agile process because by the time we started KarmaCam, Bo had his code generator working. And so we generated the MongoDB that holds those videos and the Node.js interface that glues together our mobile app and our web app. So it's now running on AWS EC2. This is a typo. It's about 75 students. Here's the hard part with projects the way I've been doing them, and that is that I am running about 95% student turnover, developer turnover every 3 months. A lot of this stuff isn't too hard. Dealing with a completely new set of developers every semester is hard, okay? I don't recommend it. But this was we got 25 students this semester. I think 2 of them are doing OPT with me, so they were with me last semester, but everybody else is new. And it's taken me most of the first month of the semester just to make sure everybody's got the right code baseline to work with and that they have some idea what they're doing. But we kind of evolved this 3-phase proof of concept, MVP, release 1 pattern on this project. We started working with the visual model sprint plans. And this app is now about to go commercial. We're actually tomorrow, I'm going downtown to LA Metro headquarters at Union Station, and we're about to kick off a proof of concept project. LA Metro they run all the buses and the Expo line and all that stuff. Well, they have bus-only lanes on Wilshire Boulevard, and the cars aren't supposed to be in them during certain hours. But cars park there, and increasingly they now have a problem with Uber drivers who are doing drop-off and pick-up there. And so they would like to get license plate numbers of these cars. And so we are going to be trying to use KarmaCam for this purpose. And then the other thing that's happened is that we've decided that we really have to do machine learning. So I have 15 students doing machine learning on KarmaCam this semester. This was our initial database that we code generated. And then this is kind of the sprint plans. This was the prototyping one. So this was the proof of concept. I want to record videos. I want to be able to upload videos to the cloud. I want to be able to report on those videos. I want to be able to review those reports. I want to be able to validate their accuracy. And this is intended originally as a system for insurance companies, so the insurance company wants to be able to query to find out which of their drivers are driving badly. So this was the second semester. I had 3 students come back from first semester to second semester, which was a big luxury for me, having returning students. But basically some of these are the same, except the stories are now a little more detailed, tasks are more detailed. So now I want a dual display showing me a Google map in one window and the video preview in the other window and the ability to switch back and forth. And this is the other thing Oslo worked on for me last semester as he was running my iOS app team. So I had a student named Kashali who was doing this on Android, and Oslo was doing it on the iPhone. So we went through the minimum viable product phase, and we do things like state machines. So we're initializing the app, we're not recording, then we're recording, and then we're uploading, and we go back and forth with state transitions and stuff like that. I like this kind of design. I like it a lot better than making a unit test fail. Last semester, I think Oslo's name actually shows up on my slides there, and there, because he was a busy guy last semester. And you were doing an unpaid internship, right? So you had more time than some of the others. Last semester, we kind of came upon this realization, if we're going to launch the system, we'd better lock our database down because anyone can hack into it right now without even thinking about it. So we had like a task force to go and switch us from HTTP to HTTPS and do a bunch of other things to lock up the database and the API. And one of the things we did last semester was we built a special emergency alert receiver app. And so in our mobile app, to upload video, you normally just tap the screen here. But if you see a drunk driver, you hit the alert. And the alert is monitored by this separate receiver app, which we've designed for use by the police. So the police can have a phone in the car and see in real time any DUI videos that come in, and they can view the video right from here. So the idea is basically calling 911 to report drunk drivers doesn't work at all. And so we're trying to improve that system. This kind of led us to the need for machine learning, because if people are driving around and they hit this button by accident, we don't want to go spam the police cars with a bunch of nonsense video, okay? So what we now need is we need machine learning to sanity check these videos and figure out where to route them. So I've got 15 students this semester, and we're doing TensorFlow, OpenCV, convolutional neural networks, and basically what we're finding is that the people that do self-driving cars have done a lot of work for us in creating and training neural net models. And some of them are published, and we can get them. And so now we're working on interfacing our database to theirs. And we're using the code generator again. So this is my machine learning team this semester. So basically, each of these green boxes represents a student, pretty much. So yeah, we're really doing it with large numbers of students working in parallel. So a couple of weeks ago, we kind of said, so here's the user story. As a model trainer, I'd like to be able to annotate keyframes in my video. Okay, so we came up with this concept for a web page where we can grab the start of the incident, grab the end of the incident, trim off the video outside of that, and then draw boxes like around the traffic light and around the car that is the bad driver, and then annotate those. So we have a machine learning training video, has an incident start image, an incident end image, an annotation. The annotation has a region of interest and some metadata. And Bo came to class, and we code generated all this. This code generator produces server-side code for Mongo and Node, and then client-side code in JavaScript, Swift, and Java. So we basically, I sketched this on the whiteboard, and 5 minutes later we have an API, and I now have a student that's prototyping this page. So lessons from KarmaCam is that I haven't really had a lot of integration problems. This three-phase approach has worked really well. The visual model sprint plans work really well. 95% staff turnover every 3 months. Oh, that's hard. Don't do it. And then our student projects can graduate into real projects. So this one's growing up and becoming a commercial venture now. So now to our last project, which is my game project, Tiki Mango. Basically, I decided if I'm going to come down here anyway and be on campus, and I have access to student developers, and it's useful for us to measure their productivity, I might as well do a game project. So I'm kind of a Hawaii fan, so I dreamed up this AR, VR game where you battle 3D animated tiki men for control of Hawaii. This is built in Unity 3D. Got about 25 students to date. I'll give you a real quick demo of it running in WebGL, because we can build not just for the phone, but also, I wish I could shrink my screen, but here's a tiki man. So he's going to stand there till I throw my fireball at him. Here it is. So I throw my fireball at him, he blows up. You know, there's sounds and stuff like that. So the tiki men now throw pineapples at you, and then we're starting to work with a tiki artist. So this is one of our artist-designed tiki men. This is a cool project. If there's anybody in here who likes to work in Unity, likes game stuff, wants to do OPT or an internship, find me. But basically, this is going to be virtual reality off-island and augmented reality on-island. So we're doing live camera stuff. And this is 100% staff turnover every semester. I've never had a returning student on this project. It's really hard. So does it work? Yeah, it works. It works for all these technologies. This is a really interesting lab that Professor Boehm has. It's allowed me to go work with 200 of you to figure this stuff out. And we're starting industry testing. There's a lot of really proven techniques that go into Parallel Agile. We're not starting from zero on this stuff. And so we expect the industry tests to go very well. And so to sum it up, if we could integrate the work of lots of developers working in parallel, we could make software projects go a lot faster. And actually, we can do this by using this domain-driven microservice architecture at the beginning of the project. And 4 years of test projects and 200 developers say, yes, it works. That's how to find me. I got some business cards if anybody wants them. Got 2 minutes for questions. But otherwise, we'll wrap it up on time.